All right, so we left off in the last video thinking about doing hypothesis testing for sample means when we knew the population variance. We'll go through pretty quickly the other two scenarios. One where not really quickly. The proportion one we'll go through a little bit quicker. Um, and then we'll look at situations where we have a population mean and we only have a sample variance known. Okay. Sorry, drop my marker cap. All right. Um, so same kind of setup as we have for the sample mean. I can do three different types of hypothesis for proportions. So a greater than, a less than, and a not equal to test, right? So greater than, once again, this word is kind of coming from that alternative hypothesis. It's what I want to test for. So is that proportion greater than a specific value? So P subscript 0 is the assumed true population proportion. If it's a less than or a left-tailed test, got a less than sign in the alternative, not equal to, or a two-tailed test, I've got a not equal to sign. Same kind of principles apply when it comes to p-values, critical values, as what we were doing for population means. The only difference is our test statistic. Every other, this is the exact same slide I showed you before. It's the exact same steps. It's just that we calculate our test statistic a little bit different, right? Because we now need to subtract the assumed true population proportion from our sample proportion and divide by the standard deviation of our sample proportion. Now, here's where it looks a little bit different than confidence intervals. So remember with confidence intervals, the best guess of what we had for the to calculate the standard deviation of our sample proportions, we had to use our standard deviation of our sample proportions. We didn't have the population proportion, so we had to use the sample as our best guess. Well, here, remember, I'm assuming the population proportion is a certain value, so that's the value that I'm going to use to determine the standard deviation of my sample proportions, right? So why am I using this, right? Because if in fact what I assume to be true is true, the standard deviation of my sample proportions will follow, will have this standard deviation. All right. So let's work through a few examples. It's going to look pretty similar to what we were just doing. So let's say I want to test for whether or not more than 15% of Indiana mothers smoke during pregnancy. I take a sample of 400 mothers and I find that 72 of them smoked while pregnant. What is the null and alternative hypothesis, right? So here I want to test for whether or not more than 15% of mothers smoke. That's my alternative hypothesis. So is that sample proportion greater than 0.15? I'll assume the opposite is true, which is that it's less than or equal to 0.15. So here I've got a right-tailed test. Right? If I want to calculate my test statistic, right, how am I going to do that? Well, what is my sample proportion here? It doesn't directly given to me, but if I know that 72 out of 400 mothers smoke, my sample proportion would be 72 over 400. That's going to end up being 0.18. So I've got my sample proportion. I've got my assumed true proportion of 0.15. I've got my sample size. I've got everything I need to calculate my test statistic, right? So how do I do that? Well, my sample proportion, population proportion, sample. It's just a matter of plugging things into our equation. There's not much else I can kind of say about these test statistics. You're going to have the formulas in front of you. What word am I looking for? The structure of them is always going to be the same. I take the sample statistic, subtract the assumed true statistic, divide by the standard deviation of that statistic. Okay. And I might write them out here kind of so we can kind of see the side by sides here in a second. So I get what? 1.68 here, right? Now, right away, I should have been able to rule out all of these negative values. Why? Because if I have this right-tailed test, the assumed true value of 0.15, I found a sample mean of 0.18. That's a certain number of standard deviations above, right, the assumed true proportion. So I should have a positive test statistic, okay? So I'm going to kind of complete this whole thing out instead of like working through specific alphas. We're going to look at the critical values for every single alpha of our conventional levels. What's the p-value of this test? And what levels can we reject at, okay? So what are we doing? Well, we're looking at our sample proportion distribution, right? It should be centered, right? The mean of my sample proportion should be the true population proportion, but here we've got an assumed true portion of 0.15. We found a sample proportion of 0.18. Right? We're then going to want to turn that into a test statistic. Right? When we did that, we found our Z statistic was 1.68. Okay? So if I want my critical, sorry, we'll do the p-value approach first. So if I have my test statistic as 1.68, my p-value for a right-tailed test, which is what we have here, is going to be the area to the right of that test statistic. Okay. So how can I find that? Well, there we go. I could use this table. If I look up that test statistic of 1.68, I get what, 0.9535. Well, that's the area to the left. I want the area to the right. So what, 0.0465, right? Or I could use Excel, norm.s.dist, 1.68, comma 1. Once again, this is the area to the left. Oops. I wanted the area to the right. So 1 minus that, sure enough, 0.0465, right? If I'm rounding the fourth decimal. All right, so what levels can I reject at? I think it's pretty easy to use the p-value approach because now all I have to do is my p-value less than alpha? Is it less than alpha here? Yes, so I can reject at the 10% significance level. Is it less than alpha here? Just barely, but yes, so I can reject at the 5% significance level, not less than 0.01, so fail to reject at that 1% significance level. Now, if I'm using the critical value approach, I want the critical values that would give me, I'm going to kind of be able to cheat a little bit here. In practice, if I use the critical value approach, I should first draw out, well, in fact, I'll do that here. What I really should do with the critical value approach is draw the critical values in first. So I want the critical value that gives me 0.1, 0.05, and 0.01 in the tail. Here's my rejection regions. So I'm going to look up these 3 different alpha values. They're always going to be the same. So notice I'm still using the standard normal distribution. So actually look at some of the work that we had already done before to find these critical values. They're always going to be, oh, this is for a 2-tailed test. Okay, I guess I'll have to redo it, right? So norm.s.inv, let's set it up so I can do it quick. I'll use a cell reference over here, right? So 0.1, 0.05, 0.01. Here's my 3 different alpha values. Here's my 3 different critical values. However, this would be if I had this area in the left tail. I wanted this area in the right tail, but it's symmetric, so it'll be the same values, but positive. So I'm going to take those 3 values. I've got what? 1.28 approximately, 1.65, and 2.33. My test statistic I would then plot was 1.68. Actually, am I mixing up my examples? Hold on. No, yeah, it was 1.68. So it is in the rejection region at the 10%, 5% significance level, not the 1%, which is the exact same decisions we made using the p-value approach. Okay, so either method will lead us to the same conclusions. Okay. All right, so keep chugging along here. So we've answered all of these questions. Let's go through a second example. So let's say I want to test for whether or not more than 50% of people actually, I have this one. Yeah, I think this is I have, yeah, okay. I use this for a reason. I like to do another one for this, so I'll just add another example after this. But let's say I want to know, does more than 50% of the population own a gun? I find a recent poll of 100 people. Sample proportion is 0.41. So what's my null and alternative? Mhm. Well, what I'm trying to test for is whether or not more than 50% of people own a gun. So my alternative hypothesis, that's what I'm testing for. So I'm going to assume the opposite is true, which is that it's less than or equal to 50% or a proportion of 0.5. Now, I found a sample proportion of 0.41. So I don't even really technically have to do this hypothesis test at all. I found evidence that supports the null. So automatically, I'm not going to reject it. But I want to work through it and kind of point out, like, even if you did work through the whole thing, you'd still come to that conclusion. So what would my test statistic be? Well, first of all, I found a sample proportion that was below the assumed true value of 0.5. So I should have a negative test statistic. So right away, I can rule out A and D. From there, it's just a matter of plugging everything in. I've got my test statistic equation. Sample proportion is 0.41. Assumed true proportion of 0.5. Sample size 100. So I get negative 1.8. Okay. Now, really, I could actually use all of my work from the previous problem. I've got a right-tailed test. If I have a test statistic of negative 1.8, right? That's over here, right? I'm nowhere close to my rejection regions. I know that I'm not going to be rejecting. And in fact, what would my p-value be? Well, it gets kind of weird here, but if I'm looking at a right-tailed test, our p-value, remember, was the area to the right of our test statistic. But if my test statistic is now negative 1.8, the area to the right is going to be huge, right? So I can still find it, right? So I can look up negative 1.8. Oh, double click. There we go. I can do this two ways, right? I can do negative 1.80, so 0.0359, but that's not my p-value. That's the area to the left. My p-value, remember, was the area to the right, so it's 1 minus that, so it's like approximately 0.96, what, 41? I mean, it's huge. I have got a crazy high p-value, okay? So we just determine we have this really large p-value. Is that going to be, so I showed you that it's nowhere close to our rejection regions, and I maybe didn't highlight that strong enough. We can use the exact same three critical values as we were in the previous example because we still have a right-tailed test and we're still looking at our three conventional levels. Right? So nowhere close to being able to reject, we get the exact same thing from our p-value. If our p-value is 0.96, what levels can we reject at? Well, that's not going to be less than 0.1, 0.05, or 0.01, right? Our p-value is greater than every single alpha. So test statistic in the rejection region, null hypothesis not in my house. So if we did find the test statistic in the rejection region, we're rejecting here, it's nowhere close, right? We can also work in the inverse as well. So I kind of showed you an example that was not the most practical or useful, but let's think about instead of the same null and its alternative hypothesis, but I want to determine what's the first sample proportion I could find where I could reject the null, right? So the way that I'll do this is here, let's go over here. So we still have this alternative hypothesis, which is that the proportion is greater than 0.5. I'll assume that, in fact, actually, yeah, less than or equal to 0.5, right? Let's say, what is the very first sample proportion? So I'm looking at this. My sample proportions should be distributed normally around this assumed true proportion of 0.5. Let me autofocus this. It's a little fuzzy. So there is going to be some value that I could see for my sample proportion. And I know that at the 90%, sorry, 99% confidence level, I could look up this critical value that would correspond to having 0.01 in this right tail. Okay. So what I'm interested in is, okay, what is this? Hey, stop it. What is this sample proportion value? Okay. Well, I know that the critical value that gives me 0.01 in the tail, I can look that up in my standard normal table using Excel or using the actual table. Once again, these critical values don't change, so that's why I can kind of remember them off the top of my head. So I know that this is 2.33. How can I prove this? How would I actually find this? Using the table, where is 2.33? 2.33, 0.9901. Well, remember, that's actually, sorry, I have the area of 0.01. I've got to show you how to find the critical value. Sorry. We wanted an alpha of 0.01. Where is that? In between these two values, negative 2.32, negative 2.33. We'll use the higher of the two, negative 2.33. But remember, we're looking at a right-tailed test. So we don't want 0.01 in our lower left tail. We wanted it in our upper right tail. So it's going to be that same value of 2.33, but positive. Or I could have said, okay, look, if I want 0.01 in my upper right tail, that means the value I'm looking at, that z value, the area to the left of it is 0.99. If I look up 0.99 as my cumulative density or probability, I get 2.32, rounds up to 2.33 again. I could also use Excel, right? Once again, I'm telling it alpha. If I wanted it to be the area in the right tail, 1 minus 2.33. Okay. All right. So I've got this critical value, and I know that there is some sample proportion that would give me that exact critical value, that exact test statistic of 2.33. So all I'm going to do is say, okay, look, what's my z statistic equation? Sample proportion minus assumed true proportion times 1 minus that divided by n. Now it's just a matter of plugging everything in, right? I know the z value that I'm looking for is 2.33. So here, 2.33 equal to, and then I've got a sample proportion. Well, that's what I'm looking for. What's that cutoff? Assume true proportion of 0.5. 0.5 times 1 minus 0.5, sample size of 100. So once again, I'll show you how I would do this. So I'm going to take, well, here, let me see if I can pull this up so I can kind of superimpose this. All right. So what I'm first going to do is calculate what's in my denominator. That's just going to be the square root of 0.5 times 1 minus 0.5 divided by my sample size of 100. So I get 0.05. Right? I'm then going to multiply both sides by 0.05. So 0.05 multiplied by 2.33, I get 0.1165. So 0.1165 is equal to that sample proportion minus 0.5. I'm then going to add 0.5 to both sides. So add 0.5 to this value, and I get 0.6165. So end up with 0.6165 would be that sample proportion. It would be the very first sample proportion. If I see anything greater than that, I'm going to have a test statistic that's in my rejection region, and I'll be able to reject. So I can kind of find what these cutoff values are and why this might be useful. Like maybe ahead of time, I'm like, well, look, let's say I had a really high variance. I might be like, well, I've got to find sample evidence that's like 70% of people own guns. That doesn't seem very likely. And it just does get, I think that this is just a different critical thinking approach to this, where even before you take the sample, you can determine what that sample statistic is going to have to be in order for you to reject your null hypothesis. Right? So that's sample proportions, hypothesis testing for population proportions using sample proportions. Very similar to what we're doing with population mean when we knew the population variance. The only other type of hypothesis testing we're going to work through is when we don't know, we are looking at a population mean, but we don't know the population variance.